Good day! Today, our group shall present our project, the Cacao Bean Fermentation Classification System using machine learning.
I am Jamaica Mohares to present Chapter 1. For Chapter 1, the presentation includes the introduction, the objectives of the study, and the conceptual background. Introduction. As stated in the Department of Trade and Industry, or DTI Policy Brief Series number 2017-09, the Philippines, having a suitable geographic location, can grow all three major kinds of cacao beans, namely Criollo, Forastero, and Trinitario. But the country's share in the global market is just less than 0.01%. There is a demand to produce good quality chocolate from high quality of fermented cacao beans, motivating several industrialized countries to further improve their harvest yield, thus being challenged by a globally competitive market to have higher processing stages. The country needs to develop an improved post-harvest fermentation and drying methods for quality protection and post-harvest loss prevention. To produce good quality chocolate, one must also have a good quality of cacao beans, and one of the key processes to produce good quality of cacao beans is the process of fermentation. In the Philippines, the conventional fermentation process takes 5 days to complete. The problem is that the environment where the cacao beans are being placed is uncontrolled and not monitored. Thus, the quality of the fermented cacao beans suffered in the process. With the lack of an improved fermentation process, the proponents proposed to conduct an experimental study whose goal is to design and develop a system with the main function of fermenting raw cacao beans under controlled temperature and environment, thus producing quality fermented cacao beans. Moreover, the proposed study also aims to shorten the time of the conventional cacao bean fermentation of 5 days into a 2 to 3 days process only. The general objective of the study is to build a system that can adequately and effectively ferment freshly harvested cacao beans through a monitored and controlled environment in order to complete the process in a shorter period of time. To be more precise, the project study specifically aims to: number 1, design and build a fermenting chamber that will monitor cacao beans under 3 varied and controlled conditions in terms of temperature and fermenting duration. Number 2, identify through MSA and design of experiment the suitable conditions of tested cacao beans. Number 3, gather necessary image data on the physical characteristics of the tested cacao beans for every fermentation level classification, namely under-fermented, adequately fermented, over-fermented. Number 4, perform image processing that includes denoising, segmentation, and color space conversion to extract the following features: RGB, HSV, and LAB. Number 5, train the following machine learning models, namely SVM, ANN, and KNN, that will classify the fermentation level with at least 90% accuracy. Number 6, design a temperature control system with integrated microcontrollers using Arduino and mini-computer Raspberry Pi module. Number 7, integrate the system to a graphical user interface or GUI that will allow users to view, access, and control the following: current temperature, fermentation level classification, and elapsed time. Number 8, test and evaluate the accuracy and efficiency of the whole system using series of tests that are validated by calculations. As presented in the conceptual framework, we presented the putting of fresh cacao beans to each chamber, as well as the experimental phase and the implementation phase as the inputs of the system, while the control system, image processing, and machine learning construct the processes of the system. And lastly, the classified fermented cacao beans as the output of the system.
Greetings, I'm Trans Mercado and I will now discuss to you the hardware of the project. The purpose of the entire system is to facilitate the fermentation process of cacao beans in a controlled manner. By focusing primarily on the systematic change of heat, the temperature inside will be regulated, and aside from this, the system can also identify the fermentation level of the batch being fermented inside. To put it into detail, the heating chamber is made from commercially available mahogany and is fixed to a metal frame. To hold them in place, stainless steel screws were used to attach the planks to the metal frame, while some parts were glued together that has little to no effect to the fermentation happening inside. The sides of the planks are tightly pressed to one another to make sure that there will be no gaps that can affect the resulting fermented cacao beans. It is to be noted that neos were highly discouraged because of their tendency to rust. The measurement of the heating chamber itself has a dimension of 1.52 meters in length, 0.515 meters in width, and a height of 0.99 meters, and that is without ground clearance. Now, let us proceed to the dimensions of the mesh tray. It has a length of 0.436 meters, width of 0.505 meters, and height of 0.2 meters. Now, the mesh tray is made from stainless steel, of which the bottom part of it has a mesh. This is suggested to us when we conducted the interview, stating that the pulp juice coming from the cacao beans must be separated, and also the pulp juice itself is a product that can be benefited on. Now here are the other notable parts: the drainage compartment, of which where the pulp juices will be drained, and the inside look of the chamber, and the inside look of the chamber with cacao beans this time. Setting that aside, let us now discuss the components used in the project. The first one would be the Raspberry Pi 3 Model B, which serves as a central processing unit of the system, followed by the Arduino Mega 2560, which will receive the incoming data signal from the installed sensors, and next would be the A4 TechViewCam PK-835G, which serves as the capturing device for the cacao beans, which will be fed to the Raspberry Pi module. Followed this is the micro SD card, which serves as a storage device of the whole system, which can be found in the Raspberry Pi module, followed by the DHT11 sensor, which is the temperature and relative humidity sensor module, followed by the relay, and then the power supply, which will be responsible for supplying power to the designated chamber. Next, we have the solid state relay, which has a 5 ampere rated load current, and then the next would be the voltage terminal block, which is used to join multiple wires without the need of intertwining them all together, and then the next would be the bulk converter step-down module, which is used to protect the whole system from short-circuiting by limiting the current and self-recovery. To the last three, we have the windshield wiper motor, which will clean the viewing area of the camera when taking pictures for the assessment of quality. Next would be the heating element, which is a nichrome wire responsible for heating the chamber. This placed inside a ceramic enclosure to prevent it from sagging. And finally, we have the 7-inch touchscreen, which serves as the screen from which the user can control the system and view the inside of the chamber. After discussing the components, let us visualize the placement of this inside the chamber. First one would be the touchscreen, which is placed in front of each corresponding chamber. Next would be the sensor placed above the mesh tray, and then the heating element, which is placed between the tray and components above that are equidistant to each other. For the other components, we have the placement of the windshield wiper and motor, the solid state relay, the Raspberry Pi 3 Model B, the camera, the voltage terminal block, the buck converter step-down module, the power supply, and the Arduino Mega 2560.
The block diagram shows the input, process, and outputs of the system. The inputs, which are the TFT display, camera, and the temperature sensor. The microcontrollers that will serve as the heart of the components are the Raspberry Pi 4 Model B, partnered by the Arduino Mega 2560. and it will be the output of the results back to display and to the corresponding actuators such as the nichrome wire and the LED lights. Software. The software of the system contains three parts: the control system, the graphical interface, and the machine learning models. These three software should be integrated in order to make a fully functional fermentation system. Control system. The control system of the machine will serve as a temperature control or regulation part of the system. It will provide the heat through a nichrome wire, a relay switch to control the heat provided, a temperature sensor to measure the current temperature that will be the basis for temperature adjustments, and a power supply partnered to an Arduino Mega 2560 for control. The graphical user interface. The graphical user interface was developed and will serve as the control for end users of the system. The graphical user contains commands behind each button to be sent to the Raspberry Pi microcontroller and execute these commands in the processes. The graphical user interface can control the whole operation of the system, starting from the control system up to the machine learning algorithm to display the results in determining the cacao beans fermentation level. There are three machine learning models involved in the system: the artificial neural network, support vector machine, and k-nearest neighbors. These three models are evaluated from the data gathering by its accuracy on identifying the fermentation level of the cacao beans. The model with the highest accuracy for each level of fermentation would be used and is embedded to the software in order to identify the correct fermentation of the cacao beans.
Chapter 5: Data Analysis and Interpretation of Results. The primary data dealt with in this project are image data. The images captured by the system have undergone the process of feature extraction and color space conversion in order for the proponents to properly quantify the external color characteristics of cacao beans using the 9 features discussed in this project. The first of the 9 features pertains to the red feature values of each classification. This has been derived from the RGB color space, and it can be inferred from the data that the under-fermented classification manifests the highest value of the red feature, followed by the adequately fermented and the over-fermented. There is also a distinct difference between these classifications in terms of this feature. For the green feature values, which have been derived from the RGB color space as well, it shows that the data acquired from the captured images of the under-fermented cacao beans manifests the highest value, followed by the adequately fermented and the over-fermented beans. On the other hand, the extracted data from the blue feature values have shown some apparent deviation from the average quantities. The spikes shown in this graph indicated the samples that deviated from the average values. Nevertheless, the distinction between the classifications may still be observed. Moving on to the HSV color space, the first feature is the U feature values. The adequately fermented and the under-fermented beans depicted more varying values than that of the over-fermented classification. The system was still able to map out the visible distinguishing characteristics of the 3 classifications. For the saturation feature values, it can be inferred that the classification with the highest level of saturation is the adequately fermented, followed by the slim difference between the saturation level of the under-fermented and the over-fermented beans. The last feature of the HSV color space is value. It can be understood that the under-fermented classification generated the highest value of the said feature, which was then followed by the adequately fermented and the over-fermented classification respectively. The third color space analyzed in this project is the LAB color space. The first of the 3 features is lightness. From the graph here, it can be inferred that the lightness of the image data decreases as the classification of the fermentation increases over time. The second feature in this color space is the A values. From the given figure, it can be inferred that the A value from the LAB color space was also a reliable factor in determining the differences in the classifications that allow the system to accurately function. Despite some overlapping data among the classifications, the system is still able to characterize the beans through the established average values in the data patterns as shown. All in all, the 9 extracted features from the captured image samples have allowed the group to develop a model that is capable to effectively distinguish each fermentation classification based on its external color characteristics.
I'm Paul Stefanilitikis to present Chapter 6. This chapter discusses the conclusions and recommendations based from the designing, development, and testing stage of the entire system. The proponents designed and developed the system under limited time, hence were not able to execute and obtain accurate results from the experimentation phase of the system. The objectives of the study were not fully achieved, and the results given in this chapter were supported with the following conclusions derived by the proponents. The proposed fermenting chamber that will monitor cacao beans was successfully built following the significant aspects of the design. The experimental phase of the system for the identification of the ideal temperature for each classification of fermentation was not achieved due to sudden circumstances brought about by the global pandemic. This situation hindered the researchers to acquire the necessary cacao bean supplies, which serve as a vital aspect in the conduct of the experiment. Before the announcement of the community quarantine, the proponents were able to gather an alternative set image data representing the physical characteristics of cacao. 150 image files were acquired for each classification of fermentation, namely the under-fermented, adequately fermented, and over-fermented. An image processing algorithm that included denoising, segmentation, and color space conversion for extraction of the RGB, HSV, and LAB color space features was applied to the data samples gathered and an output CSV file was generated. All 3 of the proposed machine learning models were executed through the Python programming language in the development of the system. The proponents used the following data splitting guide for the training of the machine learning models to compare the accuracy. At the 80-20 data splitting, only the SVM model has the accuracy of 100%, while the KNN has 97.78% and ANN has 96.67%. On the other hand, using the 70-30 and 60-40 data splitting, all 3 classification machine learning models have 100% accuracy. Since only a single batch of processed cacao beans were captured, the obtained overall result for the accuracy model was significantly high. The temperature control system was tested with working but uncalibrated sensors for automatic heat adjustments since the test was not conducted before the completion of the fermentation chamber. The GUI of the system was accomplished but has not been successfully integrated to the hardware components due to the restrictions of the quarantine. The test and evaluation of the accuracy and efficiency of the whole system was not fully achieved since a fully working system was not attainable due to the restrictions of the quarantine and time constraints, which were vital factors to the project study's completion. For the recommendations, the proponents have come up with alternatives to further improve the project based on the limited number of targeted objectives. The following are the recommendations of the proponents. The materials for the hardware should be given proper consideration due to varied difficulties in acquiring certain materials, like the appropriate type of wood, such as treated mahogany or oak. Regarding this, the proponents suggest the use of stainless steel for the casing, as this is readily available and can last longer than wood. Also, the use of stainless steel will lessen the time to be consumed upon preparing the wood to be used. For the components, the proponents would recommend on investing more in good hardware as they can provide a more accurate reading and monitoring whilst being efficient. For the heating chamber, the proponents would recommend being cost-effective as the targeted market are small-time cacao farmers. Aside from this, the size of the chamber is to be considered as well for portability. For the fermentation process, the proponents recommend looking for 2 or more cacao farms in the Philippines, having more cacao experts for the deeper understanding and knowledge about the traditional process.
This is Enrico Ian Mole, and I'm going to present the project testing. Since the development of the projects has been limited by the current health crisis, which is the COVID-19, the proponents were not able to fully develop their prototype. Fortunately, we were able to gather data for the machine learning training before the enhanced community quarantine was imposed in the landmass of Luzon. Each of the 3 cacao bean classification has their own set of data, which enabled us to proceed with the training of the classifiers. The trained model has been embedded into the graphical user interface that I am now going to show you. Supposedly, the photo that the system will classify will come from the recent batch of the processed cacao beans inside the chamber. There is a camera that will capture an image right after each fermentation is completed. Since the prototype is not fully developed, and for the demonstration in this project testing, I have here a photo of each of the cacao bean classification: under-fermented, adequately fermented, and over-fermented cacao beans, captured inside the chamber during our data gathering. These 3 photos have not been used in the training of the classifier model embedded in the graphical user interface. We only have 450 photos for our dataset, 150 photos for each of the 3 classifications. The photos to be used now in this demonstration are excess photos from the data gathering that we had conducted. This is the homepage of the graphical user interface of the project study. At the left-hand part, it displays the current temperature inside the chamber, the fermentation level or classification, and the time elapsed since the beginning of the cacao bean fermentation. In the right-hand side, we have here 5 buttons for 5 different functions that will show us the different pages of the GUI. We have here the change temperature button, camera button, operation button, help button, and the about button. Let's first take a look at the operation button. Here, the user can start, pause, and stop the fermentation process inside the chamber. Each day, the temperature inside will change depending on the temperature setting, and in order to do that, let's take a look at the change temperature page by clicking this button. In this page, we can see the current temperature and set temperature indicator, and the rise temperature and lower temperature buttons. The current temperature indicator shows the present temperature inside the chamber, while the set temperature indicator indicates the desired temperature of the user. The next is the camera button. Once clicked, it will capture an image after each fermentation process, but since the prototype is not fully developed, we, the proponents, program it wherein we can choose an image from the library instead, and the selected photo will be classified by the system. Using the 3 photos I have mentioned earlier, let us see if the system will classify each one of them correctly. The classification will be shown at the left-hand part of the GUI once the photo has been processed. Starting at the first photo, which is the adequately fermented one, we can see that the system classifies it as adequate. Next is the over-fermented photo. The system is also able to classify it correctly as over. The last photo is the under-fermented one. As we can see, the system classifies it correctly as under. The system was able to classify all the 3 photos exactly of their respective classifications. The next is the help button, which shows some information about the functions of the buttons of the GUI. And the last one is the about button, presenting the description of the project study for the users to read. That would be all. Thank you.